In 1994, Auckland wood sculptor Leigh Christensen exhibited works inspired by the history of computing. Our department is privileged to house 3 of Christensen's works. One celebrates the legend of the Harvard Mark I computer known as Bessie, where the first computer bug, a moth, was caught in a relay. At first the sculpture seems simple, showing the tape reader, the relays and the moth. But perhaps Bessie herself is some kind of bug. Our second sculpture was inspired by Babbage's difference engine. This too seems straightforward until you look behind and see its spine and shoulder blades, or take a closer look at its head. But the pride of our collection is Mainframe, a dynamic sculpture that implements a computer logic circuit as a work of art. In fact, Mainframe is a circuit that adds any two 2-bit binary numbers to produce their 3-bit sum. The bits are represented by ball bearings, large for 1 and small for 0. Here the operator has set up the inputs to add 2 to 3, in binary to add 1 0 to 1 1. The operator slides the lever to release the inputs and all hell breaks loose. But after a while the sum appears, bit by bit, at the output at the bottom of the sculpture. In this case 101 for 5 in decimal. As another abbreviated example, 0 plus 0 to give eventually 0. Now that we know what Mainframe does, let's outline how it works. We have seen that ball bearings represent bits that run down channels representing the wires of the circuit. Components are needed to process the bits. Circuits may need to use many copies of their input bits. This technology requires a special component to do that job. Let's call it a fan-out. It duplicates its input. Mainframe's fan-outs are preloaded with both possible outputs. Let's zero in on one of them. By having both narrow and wide channels, the input is selected to release a copy of itself. Here our fan-out is given an input of 1. Now let's see that again in slow-mo. Here is a different fan-out with an input of 0. To get more than 2 copies of a bit, multiple levels of fan-out are needed. Mainframe is driven by gravity. So that the sculpture does not have to be too tall, some fan-outs release at a higher level. There are 3 of these lifts. They are the pairs of vertical wires. Components that may modify their inputs are called gates. The simplest is the NOT gate. The NOT gate produces the opposite of its input. It is like a fan-out, except that the input releases an output of the other size. Let's see it in slow-mo. More interesting are the 2-input logic gates. These also use wide and narrow channels to select their inputs. Firstly, the AND gate. If any small ball is received, it passes straight through, thus giving a 0 output. If the second input is 1, it is retained. However, the first 0 sets a switch in passing, so that a second 0 is caught, and only 1 0 is output. A first input of 1 is retained in a hopper, and a second input of 0 passes through. But the hopper can only hold 1 large ball, so a second large ball is allowed to pass through. Thus the AND gate produces a 1 output only when both inputs are 1. But any 0 input will produce 1, but only 1, 0 output. All gates are similar to AND gates, but with everything switched around. Thus an OR gate only produces a 0 if both inputs are 0. Here, in slow-mo, is an OR gate with inputs of 0 and 1. The components are joined by channels to form circuits. Let's see how they are put together to build mainframe. The rightmost section has output of 1 if its inputs are 0, 1 or 1, 0, but 0 otherwise. What logic experts call an exclusive OR. The circuit makes 2 copies of its inputs with fan-outs. It then forms both the AND and the OR of the inputs. It then calculates the exclusive OR using a logic relationship that we will not go into. Let's see it operating. First at speed. Then in slow-mo. Note that the AND of the inputs is lifted up as the carry-in to the rest of the circuit. The left-hand side of the circuit is simpler. Its output is 1 if any 2 of the 2 left inputs and the carry-in from the right-hand side are 1. It uses the 3 leftmost ANDs and the 2 leftmost ORs to do its job. Let's see a couple of examples. Here both inputs are 2 or 3, so the left bits are 1. The carry-in is irrelevant as the left output is known as soon as the first AND gate gives its result as 1. However, the left side is slower if the carry-in is needed to determine the result. Here, the left bits are 0 and 1 with a carry-in of 0 to give an output of 0. The middle output bit is the exclusive OR of 3 bits. It takes 2 stages, with 1 bit being passed upwards. Although the artist chose a slow circuit that reduces the amount of hardware, it still is twice the size of the right-hand side and is quite technical. Let's not go into it further, but watch the middle part of the circuit at speed to see how it is the slowest part. So that is mainframe. It is a brilliant work and it is also 100% logically correct. However, being art, it is not required to work impeccably every time. Take our word for that. It does model computer circuits well. The nature of the components, how they are very parallel but can have long paths that limit their speed.